Well, hey, I think we can start officially. Welcome back, folks. Just two of us today, but that's going to be all right. I'm honestly kind of glad not too many people decided to drive down to class. If you're not in Zoom, then I'm not too sure why I'm saying this here. I'm not really talking to you, but for the folks not in Zoom, you can always find the recordings up here later on. And that'd be just fine as well for days like these after getting through some hellacious winter storms. But before we get started today, any questions at the moment, folks? Okay, well, we'll make this class happen, even if it's just the three of us. Hopefully, we'll get some more in. We're just about done with section 3.3 on Cramer's rule. And there was a really interesting question that someone asked on Thursday's lecture about in Cramer's rule, we often swap a column to generate the corresponding entry for the solution. But there is, in fact, a situation where you would be swapping rows as opposed to columns. It's kind of a niche situation, but if you're curious about that, that's what this optional reading right here is all about. Aside from that, we're also in a pretty pivotal section in linear algebra. We're about ready to define vector spaces in full. But the good news about this is we've been talking about vector spaces for a while. Pretty much this is the analogy. This stuff all the way back in section 1.3, this is week 2, this is a vector space situation. But the trouble is we are interested in vector spaces aside from R3 or R2 or R4. There are other kinds of vector spaces that are more interesting, but they're kind of hard to work with and think about. So the nice thing about chapter 1 is all of your geometric intuition about how vector spaces should work based on everything we've done in R3 does in fact carry over to other arbitrary vector spaces, no matter how abstract they get. So that's what we're going to be taking a look at in section 4.1. There's a few documents here we should take a look at, or I should just briefly discuss. I posted these three right here, really as just review information for things we're going to be taking a look at in section 4.1. I would say this one is kind of optional reading, but it does go along with what we're going to do there. And everything below this stuff, I would consider it to be definitely optional reading right down there. If I can find the eraser, there it is. Down here, it would be certainly optional reading. But the reason I included these two is what we're doing here in section 4.1 when we define a vector space is completely similar to what Euclid did or Peano did with these axioms in these two different situations. So they're there as optional reading as well. Then assignment number 15, the due date on this one is pretty much in flux. Section 4.1 is not going to be on the second exam. We're going to put it on the third exam. And now that we're talking about exams, here's the information for the second exam. This one will be a week away from today, Tuesday, March 12th. And this is the formula sheet that will be the last page of your exam. You don't have to print it out when you come to the exam, but you might want to print this out when you're studying, just to familiarize yourself with all the things that are on this sheet. Definitely, you can count on the vertical matrix theorem to be on the exam 3 handout and as well as the final exam. But I included these two here since in exam 2, we're talking about linear transformations as well. And these are two important theorems that you'd want to connect the dots with when thinking about linear transformations. So that's the formula sheet. Like before, pretty much we're just repeating the same exact pattern we did for exam 1. If you look at this document here, we have solved these problems, but they'll definitely look different. What I did is I went from each section, 1.8, 1.9, all the way to the last one. I took out all the definitions, theorems, and left just the actual problems. And the rare occasion where I decided that problem didn't make a good one for the exam, I just took it off the notes. So you can come back here to re-practice these problems, get a good feel for your level of understanding. And if you feel like you need more and more problems to practice, there's more down here at the very bottom, sample final exam problems. This is for the whole entire course. So if you open this document, just make sure you're only really studying or focusing on these particular sections right here, up to 3.3. Well, any questions at the moment, folks, so far? Okay, well, other things to mention is this will be a standing assumption for all the exams. So I don't write exam questions that necessarily require calculator, but just in case, you can bring one just for the extra safety net, I'd say. But it would have to be those two calculators specifically. And I think at that point, well, after we complete the exam, we're going to try to grade it as fast as possible. I hope to get it back to you on Thursday of next week, but we'll see where we end up. Because after that, we'll be on spring break. We'll take a quick breather and finish out the course right after that. Well, that's our announcements. That's so far, folks. Any questions or comments at all before we get started? Okay, well, let's get going then. We nearly finished this section, but you know what? I'm glad we didn't finish it entirely. It allows us to come back, review that section, and makes a good one to discuss as well. 3.3 will be the last section on the second exam.
I do have
And
a quick
before we
question really fast.
Sorry, go ahead.
Just
You
in
bet.
regards to assignment 13, is it possible to email that to you before the end of the day today, or is it already late now that we're at today's class period?
Well, I'm really glad you made that comment. Yeah, I'll definitely accept that assignment at any time. And kind of what's going on with these due dates and the specific time here is for that time, I would probably delete that if I could actually, but it turns out that Moodle, when I set up assignment, it requires a time. In the past, I put it at 11:59 p.m., but then I started to feel bad. It seemed like I was encouraging people to work late all the time. But another comment about the due dates are these are not firm due dates in this class. Think of those as more, it's the benchmark you have to hit to be considered fully caught up. So even if something happened and you didn't get it to me today, I'll accept it Wednesday as well.
Okay. The reason I was asking is in the syllabus, it does specifically state that late work isn't accepted. So that's just why I wanted to bring it up and ask.
That's a good thing to mention. Yeah, kind of what happened this semester was I was going to stick to the syllabus, but right around, I'd say here, there's been a lot of interesting situations that's happened in this class. I definitely can't share that. I take student privacy very, very seriously. But there's been a lot of people who've had some pretty hard times in this class. So I decided when I was about here in the semester, maybe due dates won't be as firm in this class. But now that you mentioned that, what I probably should do is just alert the class. I should make a forum post and say what I said, not just in the Zoom, but to the whole class, just to be specific. So I'm going to put here as a reminder, talk about due dates being a benchmark mostly. Thanks for mentioning those issues, though. Other questions about that or otherwise?
Oh, I'm good. Thank you.
Yep, you bet. Any other questions from the class before we get started? Okay, well, we are right about here. Again, just about done with Cramer's rule. This one is still Cramer's rule. There's a problem like this one, but it's also kind of an application. Applications in this class are tough, though. If we want an honest application with Cramer's rule, we probably have to do something in engineering, something in physics, something in chemistry along those lines. But then we'd have to do a lot of background information talking about that actual subject. So when you look at this problem, you're going to have to really use your imagination to get the feel of this is a real honest application. So here's the thoughts you might have about it. Maybe you're building a system, maybe you're analyzing forces on a bridge or anything along those kinds of lines where there's a lot of complexity involved. Sometimes before the system or the model is fully built, you get equations like these that you're worried about. And oftentimes there could be one parameter or many parameters that the engineers or people in charge can change or tweak to try to refine the system. And so that's what we're looking at here. This is a very strange linear system that's dependent on a parameter S they're using. That's not my favorite symbol. It looks like 5 sometimes. But now we're wondering if this is an important feature of whatever system we're building, what will happen as we vary the parameter S? How small can we make it? Are there values we can't throw in? And that's what we're about to analyze here. We're going to determine first the values of the parameter S for which the system has a unique solution. Let's think of this as part 1 of the problem. Then after we determine when we'll have a unique solution, we'll describe the solution using Cramer's rule. So we'll make that be part 2. I'll just drop it down there as a reminder. That'll be our second thing to tie together. So really to do any kind of analysis on this, the trouble with Cramer's rule is we don't use the system of equations. We want the matrix equation. We go from there and write out the system can be expressed as AX equals, and let's do some matching on the color coding here. B was green, so I'm going to put green here. So that's what we need to analyze. So after we say that, we need to indicate what the matrix A is. So where A equals, this is now pretty much day one of the course kind of stuff. We'll take the coefficients here, throw it into the coefficient matrix A. So it's going to be 2s, 3s, 1, and a 6s. We're not solving a system, so we don't augment that matrix. We just leave it in that form. To be specific, we can say x equals x1, x2, although that's probably something you might typically skip. We want the matrix A, and we want the column vector B, most. So B is 1, 2. Coming from this point or this position in the system of equations. So with Cramer's rule, this is pretty much always the start. We want to exhibit the matrix A, the column vector B. But we're only going to work with the column vector B when we go to this part, describing the solution. For the moment, we're wondering when the system is going to have a unique solution. So that's all about analyzing this matrix A right here. So there's a lot of ways to think about this. You'll have a unique solution if this matrix has linearly independent columns, or you could say if there's a pivot in every column, or you could say if it's invertible. There's a ton of things you can say. But it turns out probably the easiest way to analyze this problem is, let's go right here in the vertible matrix theorem. The easiest way to find that is on the exam 2 formula sheet. And the determinant is a really powerful tool for us to use to answer that kind of question. So we're just going to hit it with the determinant. If it's not equal to 0, then we can find somewhere along here, we'll have the columns are linearly independent, so there's no free variables, and that's what makes it have a unique solution. So it just delves all the way back down to taking a look at this determinant function. We'll calculate determinant of A, so product of the main diagonal is 2s times 6s, so 12s squared, minus the product of the off diagonal, 3s times 1, so minus 3s. Next thing we can do with this is you definitely want it as simplified as possible. It's a weird statement because it looks simplified, but saying something is simplified is context dependent. In this context, simplified means factor it down. It's the greatest common factor of 3s. Factoring that out will leave a 4s minus 1. And this looks weird at first. We're looking for when it has a unique solution. And so I'm looking next at this, the contrary to this one. I'm going to look for when it actually equals 0, which is when it would not have a unique solution. So I'm looking at the problem points first. So let's set this equal to 0. The moment we do that, our factored form can give us a zero product property of 3s equals 0, or 4s minus 1 equals 0. Then we immediately have two values. S equals 0 from the first equation, comma, or 1/4 from the second equation. And by the way, in mathematics, it really is a literal or that goes right here with the comma, but that abuse of notation is so common that it's become just part of vernacular. A comma right there just means or. So S has these two values, but those are the problem points. If S is 0 or 1/4, this becomes non-invertible. Solutions are not unique if they even exist. And so now we have to say the solution is unique, provided. Now we negate this entire statement. This is when the solution is not unique. So we'll say S is not equal to 0. Now I wrote a comma, but that's probably better to emphasize. If we're negating this entire statement right here, and we really mean it, all of this, the thing right here that's an or turns into an and. So let's write out S is not 0, and S is not equal to 1/4. So those are two problem points on the parameter values. And again, if this is a large system people are building, you can now report to the engineers, just stay away from these values and you should be fine. You'll get unique solutions otherwise. Well, any questions at all, folks, on finding those two values? Okay, now that we have them, we can convert to the second part. We know when the system gives a unique solution, and now we need to find that unique solution. We'll use Cramer's rule to do it. I mean, you could use row reduction. That is completely fine. This is our opportunity just to practice using Cramer's rule. So here's how the process goes next. We go back to this matrix A, and just to organize everything, I think it's usually a good idea to just calculate that determinant right here and now. Well, we did. It's this. So let's take these values. They will form our denominator. And now next thing we could do is just write out the solutions. Let me scroll just a touch. By Cramer's rule, which we're using officially now, we'll write x1 equals determinant of A1B. Then divide by determinant A. We already have that determinant down. We just need to calculate the numerator determinant. And here's how it goes. Because we're doing the first value, x1, this is indicated as A1 of B, which means take your column vector 1, 2, and put it right here in column 1 of A. Then go back to your original matrix A and just reuse column 2. It's 1 and 6s. So our numerator is done. Denominator is 3s, 4s minus 1. All we have to do is simplify all this down, and we have half the solution. Any questions at all, folks, on that stage? Okay, let's see where this adventure takes us. I left the denominator here in its factored form, just in case it has a chance to simplify. It'll be more easily seen in that factorization. So next for the numerator, main diagonal will give us a 6s minus product of off diagonal, which is 1 times 2 for a 2. And then the whole thing is 3s, 4s minus 1 down below. Looking at this, best I can do is factor out a 2. Doesn't look like there's any simplification there. So I'd probably just leave the answer in that format. Again, we're done. That's half of Cramer's rule. We just need to convert over and calculate x2. Any questions at the moment? Okay, good news about this is it's a pretty methodical process. If there's x2 that you indicated here, your numerator is essentially the same, but by the red dot, you would put in determinant A2 of B then down below, determinant of A like before. Now, next thing that happens is in this determinant in the numerator, only because we said A2 of B, we'll throw the column 1, 2, that vector B, into the second column, so column 2. We still have to go back to the matrix A and use that original column 1, which is 2s and 3s. But the denominator is done. That determinant is 3s times 4s minus 1 like from before. So really, when you really eyeball this thing, not a whole lot of difference. It almost feels like you're going through sequences of deja vu when you run through Cramer's rule, because there's just a small change in your numerators to get all of the solutions x1, x2. Now all you have to do is calculate it. But we've done about 50 or 60 of these 2 by 2 determinants at this point. It becomes pretty methodical. This is 4s minus 3s. And hey, that is a like term. We ought to simplify these when we see them in the homework. Down below is 3s times 4s minus 1. So the numerator is now s. Divide by 3s times 4s minus 1. And even more cancellations. We can cancel the common factor of s, numerator to denominator, and leave a 1 over 3 times 4s minus 1. So we've got it. We've described x1 and x2 down below. You're fine to leave your answer just in that format if you like. I think actually taking these things like this and this, and jamming them in there almost makes the solution a little bit harder to look at. This is pretty descriptive with what we have down below. But any questions at all, folks, on running through that last Cramer's rule?
There's no need to factor out the denominator at the end.
On-
those, or
You mean like say distribute the 3s inside and stuff?
right.
Yeah, not at all. I'd say usually for these kinds of things, the factored form you see is usually the better form on these. But it all boils down to a stylistic choice at that point. If you did expand the denominators, you have just as good of an answer, really. Any other questions about that so far? Well, congratulations, folks. We got through Cramer's rule. This one is not going to be a huge deal on the exam. It probably is going to be between 1 or 2 questions. The one thing to watch out for, if it is a real exam question, is I'll often put down something, let me see if I wrote it in, like this on the exam. There'll be a warning to say, you really do have to use Cramer's rule to get credit on these kinds of problems. I'll try to put it in bold to make sure we see that. And I mention these things because it's really kind of rare if I put that on exam, I want a specific method. So I'll always let you know when that happens. If it doesn't tell you to use a method to solve something, everything is on the table. You can approach it however you would like. But the exam question is all about Cramer's rule, so you'll see an indication to definitely use Cramer's rule for credit. I think we've said just about all we have to say. Any last questions at all, folks, before we turn to section 4.1? Okay, well, let's now take a look at vector spaces. After this document saves, that takes us a moment. Before we jump into vector spaces, it's a good idea to look at a couple things from the past, just as a reminder. And here's one comment we did make. When we were in section 8.1, about a month ago or so, it's been a while, if you had to distill down what linear algebra is in one sentence, I feel like this sentence does a pretty good job. The study of linear algebra is really the study about a certain classification of functions, which we call linear functions or linear transformations. But this thing is curious. These are a class of functions, so as soon as you define a new class of functions, you must state what its domain is and its codomain, and they are vector spaces. They're mappings between those things. We, in fact, did define a vector space like Rn, R2, R3, and so forth, and it's all about having a rule of vector addition, scalar multiplication that obeys certain properties. That's the part we were kind of loose about. We didn't say what properties it has to obey. We wrote down things like these and just said, trust us, it really does follow all of these properties if you define vector addition and scalar multiplication in those ways. But again, all of this was really a big analogy for us, because what really happens in vector spaces is similar to what happened thousands of years ago, like say with Euclid. This is the offshore reading kind of stuff, but I think this is a good thing to look at before we jump into section 4.1. Euclid is a very interesting individual. Modern mathematicians have looked at his work, and when they look at it, some of them feel like he was practically a time traveler. Let me tell you what I mean as soon as I find the document. Euclid did a type of mathematics that started with axioms. These are statements that are non-debatable. They're just part of the system. Here are a few axioms, for example. To draw a straight line from any, oh, those are postulates. Where are my axioms? I should have oriented myself on this page before going to the actual thing. Let's see if we can just Google it. Euclid's axioms. That'll be a little bit better. Here are his actual axioms. It's in that actual Wikipedia, or not Wikipedia page, but it's buried in there. Here are the things that he wrote. Things which are equal to the same thing are also equal to one another. It's a curious statement, but he needed that to develop his geometry. If equals are added to equals, the whole are equal. Hang on. That's the wrong one. I think we finally got it. Sorry for the trouble finding this, folks. Here are Euclid's axioms, sometimes called postulates. I think that's where I lost my way. Postulate 1 is a straight line may be drawn from any one point to any other point. Everyone feels like this is intuitively true, but he needed to make that an official axiom to develop his geometry. He didn't want to say what exactly that meant. He just made that a certain thought. And everything that was developed in Euclid's geometry came from this information right here. Now, anything that fits each one of these axioms or postulates could be considered a form of geometry, and you could start studying it in its own right. That's essentially what we're doing in vector spaces. So now back to section 4.1, here are the axioms that we work on. There are 10 different axioms, 1 through 10 right here. But even before that, it starts like this. Your vector space is essentially a set that's endowed with two different operations. That set is declared to be non-empty from the very start. That's the way we avoid vacuous truths in mathematics. Things have really happened where people went to defend a thesis for their PhD, and it turned out their interesting mathematical object was a set containing nothing. So we want to avoid that right away. So we want a set with actual stuff inside of it. We call that stuff vectors, even if they don't even seem like they would be vectors normally. That's just what they're going to be denoted. You have to have a notion of how to add your vectors. We call that vector addition. And how to rescale them or multiply with a scalar. That scalar could be a real number or a complex number. We stick to real numbers in this course. We'll call that scalar multiplication. And then once those two operations are defined, everything else right here has to qualify for your system, your set. There's a couple things that are a little bit extra special. The closure properties are things that we're going to look at quite a lot in these notes. Closure essentially means that if you take any two vectors, call them u and v, you did the vector addition, that would be u plus v, you cannot ever leave the set. If they came from the set V and you added them, they must stay in that set V. So you cannot escape it, and that's what we mean by closure. The vectors u and v are now trapped and closed within the set with regards to vector addition. And same for scalar multiplication. If you grab a vector u from the vector space V, a scalar c, multiply with scalar multiplication, then c times u can never leave that set, and if it did, it was never a vector space to start. Closure requires c times u is still in the original space V. So those are some of the more fundamental properties, and everything else are just the things we like and take for granted. For example, we have commutativity with vectors. If you ever come up with a set that loses commutativity, then it's not a vector space. It could be valuable, but it's now a pretty exotic algebraic structure. We saw that happen in matrix multiplication. We found that A times B is not necessarily B times A, and that took us through a whole rabbit hole of matrix inversion just so that we could handle normal algebraic operations. So losing that property would be dire if it did happen, but vector spaces are typical things that we like to work with, so it's natural to have commutativity here. Associativity is not something we always think about as well. Associativity is things along the lines of, if you take 2 plus 3 plus 5, everybody knows what that quantity is. You don't necessarily have to associate the front two, but you could if you wanted, do those two operations. You don't necessarily have to associate the last two, but you could and do that operation first and then add 2. Associativity essentially just says, this makes sense no matter where you put the parentheses on this thing, it has exactly one value. That must always be true for vector spaces, and if you lose that, that's a pretty bizarre algebraic structure all of a sudden. Although I didn't emphasize it, this is pretty important for us as well. A lot of work we're going to do in this section, knowing what the zero vector actually is in your particular space is pretty important as well. I mean, if we're working in R2, R3, we probably know what the zero vector looks like. But vector spaces could be very different. It could be a set of functions. We want to know what a zero vector would look like in a function space as well. Let's leave the emphasis on this one since it is a very important property. And it does what you would expect it to. If we're talking about addition, adding the zero vector is a statement of no change. There's other great things. No matter what vector you come up with in the vector space V, you can find its opposite to add them together. And I should put bold here. Let's do it right here. Just want to emphasize, you can always get back to the zero vector by adding the right appropriate opposite vector. These ones right here are just the typical things from algebra that we expect should work for vector spaces. So think of this as a list of properties that we can take for granted. Well, any questions at all, folks, with the 10 different axioms of a vector space so far? Okay, one thing we won't do in this class is I'm never going to give you a set and say, prove that set is a vector space, because that's a lot of honest work. That's not really appropriate to this course. You would have to verify all 10 properties to really make that happen. But what could happen as an honest problem is you could be given a set, some set B, and you might be asked to find out why is this set not a vector space, which would mean at least one of these properties has failed. But if you're trying to show something is not a vector space, the properties you really want to take a look at are these two. Usually the properties that fail are closure, and that's the ones you're going to be looking at primarily in the homework and as a potential exam problem as well, for exam 3, not for exam 2. So here down below is just a restatement of closure for vector addition, scalar multiplication. Put this here just to emphasize that this is massive in our work for determining if we have a vector space or not. And then down below are just additional properties that you would expect from a algebraic structure. There's only one zero vector, the additive inverse is unique, and all those other things as well. Well, any questions or comments, folks, at the moment? Okay, it is a lot of stuff, but I want to emphasize one thing about all of these 10 axioms, the 5 different things on the theorem down below. It's very much like, again, when we saw all these algebraic properties. They're not things you necessarily try to memorize verbatim. It's just a list of things you're allowed to take for granted. So I feel like a lot of people would feel, even if I did put this on the exam 1 notes, you might not have really used that. And same kind of thing with, lost my place. There we go. This stuff, especially these 5 different statements down here. They're just things that we're allowed to take for granted. Well, now that we have a vector space, there's some things we can start doing with them. The notes contains a lot of examples. Some of the spaces are familiar, some of them are going to be new. But the whole purpose of everything on these notes, of which there's 13 pages, it turns out, is just to get a feel for what all of this is trying to say when we have a vector space and when something is not a vector space. And half of the notes are going to look at subspaces as well. Well, that's a lot of information and statements. We should probably pause here for a moment. Any questions, comments, or concerns so far? Okay, then scrolling down below, that's us. Down below is us now just trying to get used to what vector spaces we've seen and the new ones we're about to take a look at. So this is just a reminder that chapter 1 was about vector spaces, but we were concerned about those kinds, R2, R3, and so on. It's a vector space under vector addition, scalar multiplication, as we used it in chapter 1. But like we mentioned before, this alone could be an honest exam 3 question, maybe for Rn or maybe for R5 or another vector space. We always need to know exactly what the zero vector is, and we should be able to write it down on command, like say it's a random problem that showed up on an exam setting. So if we want a zero vector for R5, here's what it would look like. We typically write out this. The hook is just a way I indicate in handwriting that it's a vector, not the ordinary number 0. If it says we're dealing with R5, that means it has to have 5 entries, and it would look like this. 1, 2, 3, and let me try again to get that spacing quite right. 4, 5. So there's the zero vector for R5. Any questions at all in writing that one down? Okay, just an extraneous thought here. I'm writing down that vector. Another thought you might have had is R5, sure, it's a vector space, but at its heart, a vector space is a set with operations that are being given to that set. So in a real way, what makes section 4.1 honestly a little bit more difficult than other sections in this class is out of nowhere, we're picking up set theory. So in my opinion, this is the challenge about section 4.1. And so the way my notes are organized are to just face this challenge head on. We're going to have to deal with this difficulty. We might as well learn some set theory while we're at it. It won't be anything major. We'll just learn how to look at a set like this one and seeing what it's trying to convey. So starting with R5 as a set, R5 is a set of vectors that goes x1, x2, x3, x4, x5. I usually use a colon right here to signify the words such that. Other people might use a vertical bar to mean the same thing. I'll stick to this since it looks like I produced it quite a bit in the notes. So R5 is a set of vectors with 5 components such that x1, x2, x3, x4, x5 are in that set, the set of real numbers. So this set is indicated by laying down what the typical object looks like. This is a statement that just says literally, such that. And this is the property every vector here has to satisfy. We just have the requirement that the components are real numbers. But this portion right here is the requirement for set membership. In other words, you get inside this set by satisfying that information, and that's what the typical object would actually look like. Any questions about that description at the moment? Okay, well, let's take a look next. Here's a set. It's indicated as H. It has 2 components written out as a column vector, so it looks like it's a subset of R2. Here's the property that they have to satisfy. A and B are real numbers, and A is less than B. So we're talking about the set of all vectors that has this property. We want to show B is not a vector space by demonstrating closure is going to fail for at least one of the properties. But the first thing you want to get going on this is you have to have a feel for what does this even look like, get some intuition, and then we'll take a look at the closure properties above and see how they interact. So before I do anything at all on this thing, let's actually graph this set to see what it looks like. If this was a real homework problem, you wouldn't have to graph it, but if it's helpful, that might be scratch work or work you hand in. That could be something that is not a bad idea. So let's start by, again, there's 2 vectors here, so it's something we can draw. You could call this an x-axis, a y-axis. In the past, we've called this an x1 axis or an x2 axis. If these are indicated as an A and B, you could also call this an A-axis and a B-axis. So there's a lot of stylistic choices you can make. So let's look at this condition really carefully. To get inside this set, the only requirement is that your first component or first coordinate is less than your second coordinate. That means there's a division where A equals B. That's going to divide where you have things inside your set and things not inside your set. So I would probably begin by just plotting this line. Let's make it a dashed line because everything on this dashed line is not in the set because it doesn't satisfy that requirement. So here's the line.
Would that act as a sort of an asymptote then, or?
In a certain sense, it would be, in the sense that everything here, if it's a vector, would be approaching this line, but it wouldn't actually hit this line. So that's a right analogy to think in terms of asymptotes for this one. I would agree. So this line itself is A equals B. That's why it was a little bit easier to plot. It's just a 45-degree line through the origin. Now we have a second problem, and this is, again, a good kind of problem because we have to tackle set theory for vector spaces. We're going to do it right here and right now. I'm going to place 2 different vectors. Our job is to determine which vector is actually inside the set H. So here's one vector. This would be the vector 0 for first component, 1 for the second component. And here's another vector. This one goes, let's color code it just to help track through the nodes. This one has 1 as the first component, 0 in the second component, and we must decide set membership for both of these. Here's how we'll do it. Let's maybe even give them a name. I'll call this one U and this one V. So on the margin to the right, if U equals 0, 1, and you're deciding does it fit in the set, first thing you have to check is, does it have 2 components? And if it doesn't, that's an automatic no. So if this was 0, 1, 1, we're not even talking about the same set, let alone the right vector space. Then we have to double check we have real numbers. That's pretty much a guarantee. We're not doing complex numbers so much in this class. But this is the major thing we have to look at. It means we have to kind of reverse engineer. What did it mean by A? It meant first component. By B, it meant second component. So that condition is just saying your first component must be less than your second component. Coming back over here, we can say since 0 is less than 1, U is in H. So it really does belong to the set. But let's turn over to this one. The problem with this one is if we write V equals 1, 0, we can say since, again, we're thinking first component less than second component. When this time we have 1 greater than 0, it violated this condition immediately. Might as well circle that to indicate the problem. We had to have the first component less than, not greater than. So we could say, since that happened, V is not in H. So this is the setup so far. This line divides where the elements of H are and where they aren't. They are not on this side whatsoever. They are up here, all of them. So the set H can be visualized this way. Just going to do some kind of lazy shading to signify it. So this is where H lives. Any questions at all, folks, on determining the visualization of the set H or any of the set membership stuff over here? Okay, well, we haven't done too much, but we now have a visualization of what's going on with H. H is half of the plane, but it's at this kind of funky little angle. We wonder, could it be a vector space? Well, we're using operations of the typical vector addition and the typical scalar multiplication. If there were different operations, it would have had to have been specified up here. But let's take a look. It says, well, you can pick 2 vectors and add them together, and they have to stay inside V. That could be a hard property to check. For a hint on the homework, typically this one is a really easy one to check. Let's see if we can violate closure of scalar multiplication. What we're trying to do is leave the set H, and here's how it goes. C times U has to be in the set V. Instead of V, think of that as H. That's the set we're working with on this one. For any vector U in, just put H there, and any scalar in R. Well, here's a vector U inside that H. So let's say we have U equals 0, 1 in H. Now we can pick any scalar we would like. If I pick a 10, I'd be scaling this by 10, but then it would just go way up here. It'd still be inside the set. We need a different scalar. So let's say let C equal, I'll leave it up to the class. We're looking for a way to scale U so it leaves the set H. Any volunteers for what numerical value to place right there? Yeah, go ahead. Oh, sorry.
Sorry, no, just trying to visualize it.
No worries, sorry.
But just anything that would fall outside of that, so maybe -10?
Exactly. -10 would do the job on this one. So let's throw in -10. So now what we're doing here is, just like in chapter 1, we're looking for a counterexample to the statement of closure of scalar multiplication. We're trying to show it fails. But to do that, you need a specific vector and a specific scalar, and you have to run the operation. So we need to say then C times U is going to be -10 scaling 0, 1, which would then turn into 0, -10. We need to make a statement here. So let's put this one in this color, because this part is really easy to miss. We've been mentioning a lot in linear algebra, but for these kinds of problems, especially in chapter 4, it's easy to miss the conclusion, and we have to say it here. So we need to say, this shows C times U is not in H. We also have to justify our conclusion, and that would be because when we go to justify this conclusion, we really want to look up right here. I mean, all of this is great, but it was just visualization. The truth about CU being an H or not an H is all about that. The first coordinate had to be smaller than the second coordinate. But our first coordinate here, 0, is larger than the second coordinate of -10, and that's what did the job for us. So this shows CU is not an H, and that means closure of vector addition does not hold. We've pretty much answered the whole question at this point, but it's a good idea to even add just a little bit more. This is more for our own purposes to internalize what did we just do. It said, show V is not a vector space by demonstrating one of the closure property fails. We showed this closure property has definitely failed, but we should return back and just say, assert it for our own satisfaction. V is, oh, I called that V. Sorry about that. That should have been right here at H. I think I corrected it down there, but that was just an Excel extra definition. Should have been H right here. That was definitely a typo. Let's say here, H is not a vector space. But we did it, folks. These problems are actually pretty short. We made a big mountain out of a small problem. That's because we're just trying to study the set theory quite a bit while we're here, pick up the knowledge to help us go through the next problems down below. In particular, understanding set theory is so vital because we're not just looking at vector spaces, we're also looking at subspaces, and a subspace is a subset of your original set V itself. So all of a sudden, lots of set theory and language of revolving around it becomes pertinent to this topic. Any questions or comments whatsoever, folks, on getting through that one? Okay, so the short of this is you can never just cut up a plane like this and make it a vector space. If you want a vector space in R2, it's either going to be an entire line, but it has to go through the origin, or the entire plane itself would have been the subspaces or vector spaces relative to R2. But let's take another look at this. Below, I have different examples of vector spaces that we're going to start to take a look at. And we took a preview of this way back, I believe, in section 1.9. We did an optional problem that did operations on this kind of space. But now it's coming back in chapter 4, and we'll study it more and more as we run through the course. So here's our next kind of vector space. Sometimes vector spaces are not points in a plane or in three-dimensional space or so on. Sometimes they're complete function spaces like this thing. This is what makes linear algebra hard, is that I have no way to really visualize a set like CAB, because CAB is a set of all functions f such that f is continuous on a closed set AB. Well, I don't have a picture for that whatsoever, but the good news is everything that we did over here is the right analogy to think about. All the properties and things that you did in this section carry over, because R3 is a vector space in the exact same way that CAB is a vector space. They're just different in a lot of other ways, but they have a lot of familiarity. So if we're going to work with this space, here's the other things we have to think about. We reviewed the function operations. The purpose of this document is just to say, here's how those operations are defined in a function space. Scalar multiplication just means you rescale C. Take C times F. Here's the definition, C times F of X. But in practice, it's nothing major. You just take the function output, multiply it by C. Likewise, vector addition, this is nothing exotic. We're just going to call the new function F plus G. It's good to pause on that. When you see F plus G, that is thought of as one whole symbol with other parts that could go along with it. But it's just one symbol. We're referring to a new function as F plus G. The parentheses that go around it are just so we can capture and think of this as one whole symbol for the brand new function, which is being evaluated at X. And then at the right-hand side, we're just taking two outputs, and this plus is the ordinary one, adding two real numbers together. This plus is the symbol coming from vector addition. So we take those two operations, and again, here's how it looks. This has to qualify for all T and AB. Down below, the scalar multiplication has to qualify for all T and AB as well in the closed set. But this is actually not enough to determine closure whatsoever. Let's say what we mean right here. So it says, verify closure of vector addition, explain why F plus G really is in CAB. To do that, we have to do set theory. There's just no getting out of it. We go back to CAB as a set. It's all functions. It's continuous on the closed set AB. You know, this part, you already know to be true because they are defined for all T and AB here and here. So that's not the issue with closure. We have the right domain on each one of these two new functions, the F plus G and the C times F. The issue is right here. They have to still be continuous. Well, the good news is we've all taken calculus, and although if you've taken calculus, you might not have a perfect memory of it, but here's something from down memory lane in calculus class. Here's some concepts about continuity. The ones we need are in the box right here. When we say continuous, and we're talking about an interval, we're actually talking about different kinds of continuity. If we're defined on only one side of an endpoint in an interval, we mean continuous from the left or continuous from the right, using those definitions here. So back onto this interval, we want a function that's continuous on A to B, but what we mean there is ordinary continuity in the middle, only continuous from the left on A, only continuous from the, let me try again. Only continuous from the right on A. Your numbers approach A from the right-hand side, larger values. That's our weird directionality. Your function has to be continuous from the left, going up, approaching B on that end. Actually, that's not the problem either. That's just being specific of what we meant by continuous on a closed set. This author who wrote this out means that kind of continuity. There's different conditions depending on where you are in that closed set. It's actually theorem 4 that's allowing closure to really work for that vector space, making it an honest vector space. If it wasn't for theorem 4, and it wasn't for this right here, we wouldn't have had a vector space if those statements were false. So reading through this, it says, if you start with continuous functions, and we said on the onset on that problem, F and G came from CAB, so they were continuous. Then pick any constant. The following functions are also continuous. If you add them or subtract them, we're defined just the addition. Or if you rescale them, you still have continuous functions. So really all we have to do in this problem is state what we already know from experience going through a calculus class, or the reminder in that document there. Going back to this, why is F plus G in CAB? Well, let's take a look. F and G were stated to be continuous functions. So we can begin by saying FG are continuous. And so from calculus, we know F plus G is continuous. So that resolves this part right here. Coming from the condition on set membership, we were just trying to explain why that brand new function from the old functions had to be continuous. Any questions about that so far, folks? Okay, then down below, same kind of issue. That feels kind of redundant, but let's write this out in full. F is continuous. And C is an R, so it's a real number. And so, from calculus, we know C times F is also continuous. So that's what's going on with this set of functions. And this is, again, a pretty abstract departure for what we've been doing in the course all along. What it means is, if you start studying things like, say, differential equations, what you're doing in actuality is you're looking for a vector space. It's going to be a subspace in a certain sense, but it's a vector space containing all the solutions to those functions. In fact, what we look for is a spanning set, a minimal set of functions that you could span to generate things like these, which are vector spaces containing the entire solution set to your differential equation. So differential equations, calculus, linear algebra, they all are practically one subject in a very, very real sense. But any questions at the moment, folks, with either of these two properties? Okay, to me, this next part of example 3 is practically the hardest part. And these can be honest exam questions. It says, write down the zero vector of CAB and sketch its graph. That would be less likely to be an actual exam question. I don't do a lot of that kind of stuff on a exam. And I'll always indicate to you if I'm going to have you graph something. More about this part right here. We need to know what the zero vector looks like, or else we're going to have a lot of trouble working with this kind of vector space. So let's begin. There's a couple ways to write this down, but any volunteers for what the zero vector would be like essentially? I mean, it's a tough question to even ask. I guess a better way to ask it is, any inkling on what the zero vector should be in this problem? What kind of a function would it actually be?
The origin?
You're on the right track. It would have to go through the origin, possibly depending on the close set A and B. But that's the right thought. Going through the origin means you're dealing with something at zero height, right? And that's the idea with the zero vector here. Just for an analogy, we are working in a familiar space. This is what a zero vector looks like. All entries are zeroed out. Now, we go to a function space, we're working by analogy now, but it's still the right analogy to think about R2 or R3. We want a function that's essentially zero, and here's what it is. Sometimes it's indicated as a z for zero function. It's an honest function, so I'm going to say z of t. Then you have to give it definition, z of t equals 0. But that is not enough, it turns out. A function comes up with its definition like this, or its formula, but the other thing you have to supply a function is its domain. It comes with two components. So we have to say z of t equals 0. And much like with what we were saying here for all t in AB, we have to say for all t in AB. So that's one way to initialize or state the zero vector of that function space of continuous functions on the closed set. Now, if you decide or feel like that's pretty verbose, I agree with you. There's actually a shorthand for this. You're allowed to use this if you like. It's really an honest stylistic choice once again. Let's call this option 1. This one is option 2. You could just simply say z of t. That's a weird symbol, but this is read as identically equal to 0. Let me put just a note. Triple bars like these, kind of like a menu bar on an app these days, means identically equal to. Now, if this is all you write down, if I'm asking for a zero vector, or excuse me, the zero vector of CAB, that qualifies as correct. Even though it seems to contradict what I said earlier, I said you need a function and its domain. But if you write identically equal to, we look to the implied domain. This means 0 everywhere, and what is everywhere? It would have to be AB. So you don't really have to state this anymore if you decide to use this notational device. We still haven't sketched its graph, but any questions, folks, about option 1 or 2? Okay, I feel like this is important enough. Let's just slap it with a color coding. By zero vector, we mean either that one or that one. And if we were to graph it, I mean, that's kind of a challenge because we don't know where A and B is. So we'll just do a kind of an abstract graph. I'll put down a number line that goes AB. I do not necessarily know where the y-axis is or vertical axis at this point. I'll just slap it down somewhere. It's not guaranteed any longer that this is the origin, but you can think of this as a picture in quadrant 1 if you'd like. And here's the function. Goes from A with a solid dot because it takes a value of 0 at A and same at B. And this is all it does. It's just the 0 function, so it has height 0 everywhere, and that's its graph. Nothing too impressive, but there it is. Well, any questions at all, folks, discussing this wild new set, CAB, vector space? Okay, well, this is about as abstract as it can get, but keep in mind, every single thing that we did in chapter 1 can be redone for CAB. Issues about spanning, linear independence, all those kinds of things come right back and they work for these kinds of things as well. We'll see some of that in chapter 4, but we're not going very, very deep in this direction. This is an introduction to linear algebra. If you're interested in this stuff, here's a subject you probably might want to take another look at. This is studied extensively in a subject called functional analysis, where we look at vector spaces that have infinite dimension. That's what makes this one weird. It doesn't have a notion for dimension like R2 being dimension 2 or R3 being dimension 3. This one's dimension is infinite, a pretty wild topic out of nowhere. But because this one was so abstract, let's make it concrete and take a look at these vector spaces. These are the polynomial spaces. There's several kinds we're going to look at, but these ones are actually more familiar than you'd believe. Pn is the set of all polynomials of degree at most n. And my claim is we have worked in this polynomial space all of chapter 1, we just might not have really said it directly. I'll tie down that comment below. There is an actual literal isomorphism between Rn plus 1 and the polynomial spaces, meaning they are exactly the same algebraically. But that's only true if we define the set exactly the way we mean, and the same with vector addition and scalar multiplication. So we'll define our own operations below on these set of notes. But first, let's take another look at this. Pn is written in kind of a similar way you might see Rn being written. But for some reason, our author likes to put the n down below as a subscript. That's just his stylistic choice right there. You might find other books where it's a superscript. But now when we say n, we mean polynomials of degree at most n. Because they have degree at most n, the typical polynomials you'll see inside this set, they could be called p, but they're defined as p of t, and they'll have a term with t to the power of n inside. with a coefficient a and multiplying, the powers descend one by one. Honestly, the definition of a polynomial is always pretty ugly looking, but it is what it is. That's your arbitrary nth degree polynomial. We go all the way down to the constant term a naught. And the only conditions are an through an minus 1, all the way through to a naught, have to be real numbers. You know, that part alone is kind of a hint on what's going on here. When you look at that statement, it looks an awful lot like saying this: an array of entries arranged however you like, such that each one of the entries are real numbers. That's how R5 would have looked like. If you go to Pn, the only difference is all these entries that could be real numbers correspond to a power function to the right power. So that's the set we're going to be working on. Any questions at all, folks, with this set Pn? Okay, well, at the moment, it's just a set. It becomes a vector space the minute you define this and this. So let's do it ourselves. To help out, I've already defined P and Q down below right here. We just had to come up with the right scalars, an through a1, bn through, or a naught, bn through b naught. So P of t is defined in this way, and same with Q of t. We also grabbed an arbitrary scalar r, so think of those all being in scope for these two properties. Vector addition is indicated this way, P plus Q of t, and in some sense, that should feel pretty similar to what we did in CAB. These are functions, so they would belong to a function space. Only difference is the domain here is all real numbers, not a closed interval from a to b, for example. But P plus Q of t would look like this. We go to the first entry, an, for the P function, add to it the first entry for bn from the Q function, the Q polynomial. That corresponds to t to the power of n, so we just multiply t power of n. Algebraically, all we've done is we took P of t, added to Q of t, we're combined like terms, and there's the first term. Do that a whole bunch of times, so dot, 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 until you get to a1. Take a1 plus b1, multiply it by t. Then we're just taking a naught plus b naught. So that's the evaluation of P plus Q for vector addition. Again, there's a really strong analogy here. If you had, say, P equals 1, 2, 3, and Q equals 4, 5, 6, well, you could say that's t cubed plus 2t squared plus, or let me try again, t squared plus 2t plus 3. You could think of that as a polynomial. This would be 4t squared plus 5t plus 6. You could think of that one as a polynomial. And P plus Q would be just, well, add up the corresponding entries. I'll leave it in this form just because I want to emphasize we're just adding up the entries. But that's literally what we did here. We just took the entries, added them together. In this way, we are looking at an isomorphism. The algebra that we did here is no different than the algebra you did all the way back here. We keep going to this section because this was the real deal. This was vector space operations right here. Well, that's how the vector addition goes. Scalar multiplication is nothing special either. We just say take C times P at T. And all we do is rescale all the values here. Algebraically, that's just the distributive law. But linear algebra, it takes on a special kind of view. This is C times an times t to the power of n plus all the way down to C times a1 times t plus C times an. Again, this operation, all it did was scale all the coefficients, not different at all than this one, scaling all the entries of a vector u. So that's kind of a curious result so far. But in the polynomial spaces, that's what the operations look like. The good news is it's saying we're just using the ordinary algebra when we define that addition and that scalar multiplication. Any questions at all, folks, on these so far? Okay, well, the next thing we can write down is the zero vector, but it's also nothing too special. It's much like what we did in the function space. We could either write z of t identically equal to 0, or we could say z of t equals 0 for all t and r. If you wrote it this way, there's a domain that was implied. How would we know what the right domain is? It would have to be in the scope of the problem we're working on, and we would go right up here. The t had no restraints whatsoever, so we would think of that as being all real numbers. And so the zero polynomial down here just evaluates to 0 for every single real number as well. So that would be the implied domain on this one. Well, that's working through these kinds of function spaces. Last thoughts I want to leave with before we call it a day is the space Pn is definitely isomorphic to Rn plus 1. But there's a bit of a catch about this. Later on, we're going to be talking about dimensions. We would say something like dimension of R2 is 2. We have not yet defined dimension, but we're getting really close. And intuitively, I think a lot of people would agree the plane should have dimension 2. We would also say dimension Rn plus 1 should be n plus 1. And the reason I put Pn here and Rn plus 1 is because the dimension of Pn, and I wrote that as a superscript, let me fix it. I try to match the notation that you're going to be reading, since, I mean, that would be weird not to. This dimension is n plus 1. That's kind of a surprise, and that's also how our author defined n on this one. The reason it's one higher is because of the A naught. We have not n entries, we have n plus 1 entries due to that A naught right there. So what made them isomorphic was less about the nature of these vector spaces, but more they had the same dimension. This is one of the reasons why dimension is a very important definition in linear algebra. It turns out any vector space of finite dimension that has the same dimension is isomorphic to that. So if you have a finite dimensional vector space, what you want to find out is what is its dimension, because it'll tell you every operation you're doing here was no different than just this. Just find the right dimension to match it up. Well, any last questions or comments, folks, with the conclusion for today's work? Okay, when we come back to this stuff on Thursday's class, we'll be taking a look at the new definition. Subspaces are a little bit more tricky, and the analogy with this is working with subspace definitions is, in some sense, dealing with the same difficulty of working with this definition right here. Once I find that definition, there we go. Gotta go to the right page of notes. The subspace definition is much like this definition here in a certain sense. The algebra and the work we'll do with that is pretty similar to all the kinds of things we did with determining if something is linear or nonlinear. But it gets trickier because now there's more conditions we have to work through. And this is a problem we'll take on directly more often than we did with the linear transformation kind of problem. So it all comes back to closure. That's why we're harping on it so much. If you think about closure, vector addition, and scalar multiplication, when you read this section, you're on the right track. Those are the major things to focus on. Well, have a great night, folks. Drive safe out there, and I'll see you all in Thursday's class, provided we don't lose power and everything like that due to winter storms.
Thank you.
Yep, have a good one.
Thank you.
For some super screenshots, sorry, I forgot that you did that last time. Oh, yeah, no problem at all.
I hope the winter storm wasn't too severe for you.
No, it wasn't too bad. I was short of minutes, so
Awesome.
nothing yet.
Yeah, I heard the Pocatello got it bad too as well.
Yeah, actually.
So realistically, in the exam environment, when we're asked to find if something isn't a vector space, we're told that and we have to prove it. That's gonna typically be due to closure.
Exactly. I'm only gonna ask questions that are direct about closure.
Okay.
And another hint I mentioned is, I usually ask questions where the property that fails is. Oh. I actually made a mistake right here. The property that failed was scalar multiplication. Let me put a correction there. But that should have been correct in the notes as well. Glad we talked about that. Yeah, I usually ask questions that are direct to those two properties. And usually I ask a question where this is the one that is probably going to fail as well. Well, have a good one.
Thank you.